This presentation, I'm going to talk a little bit about what happens to data as it is flowing inside and outside of your CAD tool. I mean, most of you guys are probably all board designers, and board designers typically tend to live within the little box of schematic and board, but the problem is that you have to deal with data coming into your system to build schematic symbols, footprints, all that kind of stuff, mechanical interaction, and eventually you're going to spit out Gerber data in a drill file, and you're going to throw that through the fabricator, and you're going to give that to your assembly house, and you hope to get a board back. And typically that stuff gets done on a Friday evening just before closing time, and we all like to go on, on weekend, and 15 minutes after you went home, there's that ring on your desk or on your cell phone. We can't read your data, or we have a question because something went wrong. You walk in on a Monday morning expecting to see a board on your desk, and there's a little blinking light on your answering on your desk, or there's an email that says, we didn't move forward with the build because we have an issue with your data. You just lost 2 days. That's not good. I mean, we like to move fast. So I'm gonna go over a couple of things that can go wrong and a couple of tips and tricks how you can avoid these problems. And some of these problems are not always obvious. I mean, we may not think about certain things that can happen. So a design typically starts off with somebody has an idea for a product, and it just goes south from there on, because that idea has to be translated into a schematic, and that schematic is going to start pulling information from procurement, price, costing, budgeting, supply chain. Somebody will have to make a symbol for some of the parts that you're using. You're going to pull in data sheets that's going to end up in a library somewhere. Your schematic will have to be linked to footprints, may have to be linked to mechanical 3D models that has to come from somewhere. And that's all going to end up on a layout, and that layout tool is going to pull in even more data. You may be doing thermal analysis, stress analysis, power grid analysis, things like that. So that's all stuff that is flowing into your design. When your design is going out, your CAD tool or whatever system that you're using is going to pull in even more data and spit out another set of data that's going to go to other people who have to pull that into yet another tool that is running on yet maybe another operating system. And they're going to massage something, and they're going to bring in other data that needs to merge with your data to do what they need to do. So I'm going to touch a little bit about these boundaries of data exchange and what the possible problems are and how you can preempt any of these problems. So there's a couple of boundaries. There's not only the machine-to-machine boundary where you just exchange files, but the first problem is you have a man-machine interface. I mean, you have an idea that is living in your head that has to be translated into something that lives in the computer. Now, a computer is a fundamentally stupid piece of equipment. It doesn't make any assumptions. It doesn't think. It just does things literally. So if you don't tell it exactly what you want in an unambiguous way, it ain't going to be right. All right. So it is important that what you are inputting as data into the machine is right and formatted in a way that there is no wiggle room, or else trouble is going to arise. Then you have the machine-to-machine interface where all these files and all this data is traveling between various different systems and software systems, filing systems, databases, whatever. That's another can of worms. But eventually, that data is going to come back out of the computer into a human-readable format, meaning that you're going to have documentation, you're going to have hard copies of schematics. Somebody in the lab is going to troubleshoot, debug the board. They're going to be looking at hard copies, and there may be something going wrong there, and somebody somewhere is going to interpret something the wrong way, and you're going to lose time and money because of some little detail that was overlooked. So the goal is no room for interpretation, don't make any assumptions. And try to eliminate all the scope for any kind of these miscommunications happening. So first thing we're going to look at, component values. There's the first problem is that there's multiple numerical systems in the world. We have the US number system, and we have Europe and other parts of the world where the comma and the period have a different meaning. For a US system, the dot is a period, but in Europe it is a it's a multiply divider. It's a multiply indicator. So 1,000 is not the same as 1.000. So if you're going to start throwing data across the Atlantic Ocean, you got to be aware of that. Case in point, there was actually on the Altium forum a question from, I believe it was a guy in Switzerland that had a vault installation, and he had pulled in a bunch of library files coming from the same company that he was working for, but the US branch, and they migrated a bunch of data over, and he had a question that says, all my resistor values come in wrong. They're totally weird, and they couldn't quite figure out what was wrong. And I'm from Europe, and I kind of, in the back of my mind, I knew about your operating system has what they call a locale setting, where you tell the OS, the operating system, what you're using as the decimal marker. And I suggested to told the guy, said, switch your operating system to using US locale, pull in your data, and then switch it back to European locale. That solved the problem. So there is a first gotcha. Something simple as a decimal point or a comma can goof it up, and your 1 mega ohm resistor becomes a 1 ohm resistor, or worse, a 1 milliohm resistor. And good luck troubleshooting that on a bench. It can take you a little, because according to the bill of material, everything is correct. It's just that the machine interpreted it wrong. Can happen. Data parsers are not all written the same way. I mean, if you have a 2.2 microfarad capacitor, if your locale setting is wrong, that can either turn in 22 into 22 microfarad or worse. You get that phone call from your assembly house that says, I can't source a 2 microfarad capacitor. Well, it's supposed to be 2.2, except that the input parser in a computer, what they do is the first non-numerical character, they stop parsing the string. So that comma 2 UF that just got rejected by the machine, and the machine said, I'm looking for 2. And the assembly house goes, we don't have that. But now your production is stopped, and you get a phone call, typically when you're not in the office or you're not available, and you're stuck. So things to think about, and it goes worse than that. Some people use, let me see if this works. They try to be smart, and they go like, well, we have 1% resistors and 0.1% resistors, so what are we going to do in the library? We will indicate the precision using, trailing zeros. Well, guess what? What if that period disappears? Your 1K resistor becomes a 100K resistor, or it becomes a 1 mega ohm resistor, just because that one little character fell off somewhere. You print this out as a hard copy, and on a laser printer, that little speck of dust, if you scale your 11 by 17 onto an 8.5 by 11, that period may disappear. You may not notice that. Somebody who's hand assembling the first prototype is going to stuff the wrong part on the board. Or the laser printer may have been dusty, and a speck may have magically appeared in there, and then it goes wrong the other way. So there's issues with just numbers, okay? And then there's other things like the special characters, like the ohms character and the mu character. Not all font sets have that. So if you're gonna put that file somewhere on a computer system that does not use the same ISO character set or even the ASCII character set, you will end up with these little smiley faces and funny characters in your file, and somebody's gonna raise an issue and get on the phone and say, hey, what is this? I don't know. Again, assembly production stoppage, delay. And then the last thing, capitalization. Some tool sets are not aware about uppercase and lowercase, and they may translate everything during import to the same case. They may convert for ease of treatment everything to uppercase. So your 22 milliohm resistor becomes a 22 mega ohm resistor. Wrong part ends up on that was supposed to be a current sensing resistor. There's not going to be a lot of current flowing through that resistor. So your power supply just doesn't work, okay? So what can we do about that? Well, we're going to use a couple of rules. We're going to try to come up with a character set that is case insensitive and where there is no wiggle room for interpretation. Now this is sometimes called the SPICE notation because the people that originally developed the SPICE simulator tool, they kind of thought about that and they came up with this notation. So it's based on the international system of numbering, but we're going to restrict ourselves to the engineering powers, meaning power of 3, power of 6, power of 9, and the negative equivalents. We're going to make everything capitalization agnostic. You know, the SI system officially, they have uppercase for multipliers and lowercase for dividers and stuff like that, with the exception of a few like hecto and deca, which we don't use anyway in electronics engineering. So we're going to restrict our character set, and we will use the letters T, G, M, K for the multipliers, which is tera, giga, mega, and kilo, and for the dividers, we're going to use U, N, and P for micro, nano, and pico. Anything else is off the table because there is a risk for misinterpretation. If we start, well, what about milli? We want to use milli. Well, the problem is that the M could be misinterpreted. It could become mega or milli depending on the case. So we're not going to use milli. We're going to write such values in a different way that they'll become unambiguously. So a couple of examples. 1M8, the M means mega. So we replace the period or the comma with the multiplier character. 2U2 means 2.2 micro. If you have to have milliohms, you just write it as 0R022. That is unambiguously 0.022 ohms. If it's a capacitor value, 0F022, that's 22 millifarad, which is a really big capacitance value. And what about, you know, is there possibility for femto and farad to be confused? We're not going to be using femto. We do the same trick like for milliohms. 220 femtofarad capacitor becomes 0P22. It's 0.22 picofarads. Femtofarads are really unusual unless you're dealing with really high frequency circuitry, and even then you very rarely encounter actual components with such small values. So using these simple tricks, you eliminate the problem of locale, you eliminate the problem that some value is going to be interpreted wrong at some point in time. Most of the computer systems and most of the electrical engineering programs do understand that notation because, like I said, this comes from the SPICE world where they first came up with this idea, and it solves a lot of problems. So there's also secondary parameters to components. You have working voltages, tolerances, wattages. So what are you going to do with that? Same thing for voltages. You're going to use the letter V to indicate where your period or your comma, depending on your locale is. We're not going to use trailing characters to indicate tolerances or whatever, because if that period disappears, we're off by an order of magnitude or worse. So that is off the table. We don't do anything like that. And then the other thing is that even if you were thinking about doing that, okay, I'm going to use one trailing character, that's 10%, 2 digits is 1%, 3 digits is 0.1%, but there's also 2% and 0.5% resistors, which you can't encode in that system anyway. So it's useless to even go that way. Wattages, try to encode those as fractions. People, it's easier to think in terms of this is a 1/8 watt resistor as 0.125. What is that? That's a 1/8 watt or 1/4 watt. Or people think in terms of it's a quarter or third or a tenth of a watt resistor. And it makes it all, so if you do that kind of notation, you're not going to get any confusion between somebody read the wattage and thought it was actually the value of the part, or vice versa. You make the scheme of your string encoding substantially different enough that you can tell them apart. Now, file names. That's a big deal too, because eventually that data that is being created in your CAD tool has to end up somewhere in a filer. It has to end up in a computer system, it has to end up in a database, and things can go wrong because you do not always know what that internal software is going to do and how it's going to create the file names. Case in point, I had an issue in Altium Vault. We're running our Vault on an Oracle system, which is a Solaris Unix-based platform. And NXP Semiconductors, they have a part number that says BC847/B. So I created a part number called transistor-NXP-BC847/B. When I committed to that, the Vault, the tool wants to create a schematic library file, and it uses the name of the part as the library file. That / that is in there, that's a path indicator. So my file did not end up being named transistor-NXP-BC847B.schlib. No, there was a path created called transistor-NXP-BC847B, and in that subdirectory there was a file called b.schlib. Well, guess what? When I went back to retrieve that file, it said I can't find a file. Because the input parser that has to read the file treats the path names differently than the algorithm or the routine that wrote it. And the guy the routine that was trying to open it was looking for a file called b.schlib in the transistors folder. It didn't realize that the subdirectory had been created because there was a path indicating character in the file name. We didn't think about that because under Windows, that's not a path indicator. It is under Unix, and the filer was a Unix machine. So be very careful when you're naming things, because some other computer system may be treating your data and maybe something may go wrong. Your file may get misplaced or become unfindable by the system, even though it's there. It just can't find it because it's reading something wrong. So other things, if you're from Germany or you're from France, you have decorators over certain characters. You send it across the pond and you have the same problem. We don't have those characters. They come in as something else, and the computer says, I can't find the file because I'm looking for a different name because the fonts had changed. So what do? Save characters only. Make everything uppercase, lowercase agnostic. We're going to use uppercase alphanumerics, letters A to Z, characters 0 to 9, underscores and hyphens, nothing else. Because they may be missing on the font set, they may be wildcards like an asterisk or a question mark, they may be path indicators, they may be volume indicators, you don't know. Those things are safe across all computing platforms. They're not going to be misread. So other things, how are we going to name symbols so that they're easily retrievable? And there's a problem because some parts are available in multiple packages. I mean, like a simple op-amp can be available in a SOT23, SOT323, and an SO8. How do you keep them apart? Well, even these two guys, they both have 5 pins, but the dia actually sits 90-degree rotated, so the pin numbers are different. How do you keep the symbols interchangeable? Because somebody at some point in the design may want to downscale the size of his board and say, I'm going to change my SOT23 by SOT323s. How do I keep those things apart? Well, make sure in your library that you're not just calling out, it's this part. Encode the footprint in the name of the part. That way you're going to be guaranteed that your link up between your schematic and your footprint is going to be intact. Because again, that data at some point is going to leave your CAD system where somebody's going to look at it and not going to realize that, oh, this guy is using a SOT323 and I have only SOT23s in stock and actually the pin numbers are different. It's leave a marker behind that, in this case, the human that has to look at the bill of material and load the pick and place machine has some feedback about what could be wrong. Yes?
So So you said put that footprint in the name or
in the name of the symbol. So I encode actually the name of, in my library, I will have op-amp-ti LM741-SO8. I will have the same symbol dash SOT323 because the pinning is different. My symbols are made in such a way that if you swap one out with another one, they come in exactly the same coordinates. The pin numbers do change. So for your schematic design, it's really easy to swap one part with another. Nothing's going to shift on his design. The pin numbers are going to, the pins are going to be, or the functional pins are still going to be in the same spot, but the numbers are going to change. So he's not going to run into a situation where he changed the part and his part is now somewhere in a corner of a schematic and he's got to fix his schematic.
The challenge with such a long, meaningful name is also that it takes up a lot of space on your schematic if you're going to put the MDN on. If you're going to put
No.
for your component.
Okay, so you don't, this is the name of the file on the disk or the name of the file in the library. That's not what's going to be shown on your schematic. That is not your, in Altium talk, that is not your comment field. Your comment field will still say LM741. It is actually the name of the part in the library. So if you're browsing the library, you immediately see, oh, that's the SO8 flavor, that's the SOT23 flavor, that's the SOT323 flavor. It's not what's shown on the schematic. Yeah, I agree, because you end up with strings that are enormous. And so, yeah, there's a distinction in that.
That brings a question about next volume.
And I know that some operating systems is 26 characters and you're out of luck, but that's, yeah, you have to be careful about that. That is still one of the restrictions.
Actually, you have to be careful because one side effect of the 250 supplement is for the total length, so you have to go back to the so
I know.
I've been caught on this. The levels, like my directory, working directory.
Yeah, and the problem is when you zip up that directory and you give it to somebody else who unzips it in a different folder, and then all of a sudden the OS says, file name too long. What do we do now? So yeah, tricky situations. So a couple of examples. You know, I have, like I said, I have encoded, like for an LM311, there's an SO8, there's a SOT23 flavor. I have a bunch of genetics, like a diode genetic where pin 1 is the cathode, pin 2 is the anode. There's another one which has pin 1 as the cathode, 3 as the anode. So it's very easy to, I'm trying to reduce the amount of flavors of parts in my library because it becomes a management and a searching nightmare. So you can, there's a couple of tricks you can employ. Sanitize any of these names, you know, no special characters, no nothing, just uppercase numbers and uppercase letters and a dash and an underscore and you're safe. Try to keep it. Other problems, designators. You know, there's people, you have a switch on the board, some people will call a switch S something in a schematic, other people will call it SW in a schematic. The problem is if you start mixing designator types, the people who have to load the pick and place machine will find two part numbers with different kinds of designators. They typically sort the bill of material by designator type. So now they will actually, and I've had this happen, they loaded two rolls of the identical same part onto the machine. Because one group was called S something and another group was called SW something, even though they were the same physical part. But they were asking me, we need two reels. No, you don't. But they said, yeah, we do, because it's a different designator. Pick one, stick to it. Don't mix them. Okay? And then another common, so there's a couple of governing standards. You can actually go and read those, and some of them are aging a little bit. Another common mistake is it J, K, or P for a connector? Well, there's actually a standard. J is a jack and P is a plug. And IEEE defines a jack as the least movable part in the assembly, meaning the part on the board is always J. The part called P is the one that sits on the cable that plugs in to the jack. So that is another commonly, that's the IEEE list. There's more than that. I mean, Some of them are going to be non-standard. You want to mark those things very clearly so that your fabricators can pick those out very quickly, like where are my fiducials? I include my fiducials in my bill of material because the people that are going to be parsing the pick and place file, they want to know what are the coordinates of the fiducial, even though that's not really an actual part, but the pick and place machines like to know where your fiducials on the board because the optical system is going to line up your board to the fiducial. So by having that actually as a part in my schematic, it travels with my bill of material, and the people who are programming the pick and place, they have the coordinates. It sits right there in the file that's going into the pick and place machine. They don't have to call me, hey, where are your fiducials? We need the coordinates. They are in my pick and place file. Same thing with coordinates for mounting holes. Then you have the people who make the test fixtures and make the flying probe tester programs and the board tester programs. Where are all my test points? Well, my test points are actually encoded as a part in my, it's a non-placeable part, but it does reside in my pick and place file, and it resides in my bill of material. You can very quickly filter them out, and you have the coordinates. Yes?
So you say unplaceable, like you have to mark it as no, not fitted?
Yeah, so you create a component that's basically it is a bill of material, but it is a non-placeable, it's a mechanical component. So it will be ejected in your pick and place file, it will be ejected in your bill of material. In your bill of material, you know anything that's labeled TP as a test point on the board, I can just delete those. But because it sits in the pick and place file, the people who make the test fixtures have the coordinates. Anything in the pick and place file has the coordinate and top or bottom side, because if you have a double-sided test fixture, you need both. So you eliminate that phone call that says, well, we're supposed to build a test fixture. We need a coordinate list. Well, it's already in my pick and place file. I don't have to worry about it. When I design my schematic, it's going to be in the output. And then another thing which is we get commonly burned on is net ties. So many times we get phone call that while they were inspecting the Gerber, they have collisions on the nets because we used net ties in our schematic to connect the analog ground to the digital ground somewhere. You get the phone call, well, we parsed the net list and everything is called G and D. We don't see A, G and D, we don't see D, G and D. Well, create your net ties as a component. Again, they're going to show up in your output. Not only are they going to show up in the output, you will get the coordinates where that thing resides on the board. So the people who are looking at the Gerber file can immediately go to that coordinate and see, okay, that is where the net tie is. And then they can inspect the two nets and they can tell their post-processing tool how to carve it up so that it doesn't become a problem running on the tester. That's another thing. Yes?
So you want the net ties to show up in the BOM or not show up?
I put them in the BOM, I put them in my pick and place file. Because again, the post-processors want to have the coordinates. And it's not always, and if you only give them Gerber files, there's no coordinates. If you give them ODB++, there's a whole lot more information. If you give them IPC 2581, then that becomes a non-issue because that travels in that file format. But who really, I mean, how many of you guys use those formats? Everybody's still on Gerber and drill.
Is there a reasonable universal list of designators? Because where did that come from?
IEEE. Yeah, there's a governing IEEE standard, IEEE 200-315, and there's also an equivalent ANSI standard. But like I said, they are old standards. They date back to the 60s. Nobody's ever updated them, and there's a lot of types of components these days that don't have a category. Okay, let's move on. Questions and answers further, otherwise I'm not going to be able to finish. Yeah, this is IEEE. Okay, so footprints. Pet peeve of mine. IPC has very beautiful documentation. The problem is they can't keep up. Component manufacturers release so many new packages every day, every week, for where IPC does not have a category. So how do you name those things? There's no official way to name them. There's discrepancies in manufacturers as well. So many manufacturers tell you, oh, this is a DFN 16-pin package. That's not possible because a DFN can only have 2, 3, or 4 pins. Because DFN means diode, flat, no lead. it doesn't mean that it is a non-leaded. I mean, if it's got more than 4 packets, it's supposed to be called a SON. Some manufacturers are really bad, and they even violate their own standards. They will give you a nice roadmap, and they will tell you anything that we call TSSOP is 0.65 millimeter pitch or large. Anything we call VSSOP is 0.5 or 0.4, which in case TI, they have VSSOPs which are 0.65 pitch. They're violating their own naming convention. Don't trust their names. Look at the data sheet, look at the numbers, and encode them properly, because sooner or later you're going to make a board and that part's not going to fit. So don't trust what manufacturers tells you. Other things that IPC has issues with, they have been slow at releasing version C of their footprint standard. If you have things like TQFPs or any kind of component that has a thermal pad, not all thermal pads are the same size. How do you discriminate between that? Because you may have a 128-pin TQFP, but apart from TI, the thermal pad is 2 by 2 millimeter. If it's a big power device, it may have a 4 by 4 millimeter pad. That's a different footprint in your library. How do you keep them apart? So, trouble. I mean, the standards don't always have a clear dry cut solution for these kind of problems. And then you have other problems, is that certain component manufacturers are very bad with their naming. For example, on a SOT 89 up here, this comes from Nexperia, which used to be Philips NXP. They use reverse pin orders. You would expect pin 1 to be here. Well, they use a reverse pin order. Infineon does it differently. They have 2 pin number 2s, but if you go in the footprint library, oops, that actually is pin number 4, not 2 times pin number 2. That's another thing. Be very careful when you're making footprints. Make sure that every pin number is unique. Do not have 2 pads that are not connected with the same number. If ever you send that board to an autorouter like Spectra, the import fails because you can't have duplicate pin numbers. It can't resolve that. So if you don't take care of that in your library, when it comes to time to run it through the autorouter, be prepared to do a whole lot of legwork to convert your design in a format that can be read by the autorouter. You're going to have to do a whole lot of work. Be very careful about those things. And then another thing is that companies like, very notorious is Diodes Inc., which is a company that has acquired so many other companies and has acquired so many foundries that they're not compatible with themselves. You're going to buy a certain transistor in a SOT 23 package and they actually have 5 or 6 different flavors and they don't fit on each other's footprint. Some of them don't. The problem being that one transistor was actually a foundry that was acquired 10 years ago and somebody else has a different mold and the pin lengths are slightly different and sometimes they don't solder well on each other's footprint. So that is something to be aware of. Take a very, very close look when you're going to create footprints or whatever. Look at the incoming data. That incoming data may not always be what you want or what you think it is. And then, you know, we have all these different kind of footprints. I try to simplify them. There's 2-sided parts, there's quad-sided parts. And in my library, I have SOPs, QFPs, SOM, QFN, SOJs, PLCCs, and then the diode and transistor packages. I don't use names like VSSOP, QSOP, and all those things because they are arbitrary names that don't really always abide to standards. Every manufacturer labels things differently, whereas if you reduce those kind of names, you very quickly know what category or what to search for in your library. Okay, it's a 2-sided, it doesn't have any leads, it's going to start with SON. So if I do a search in my library, SON question mark, I'm going to have all the footprints that fall in that category, as opposed to having to start to fish for DFNs, SONs, VSONs, and whatever. You're searching, you know, data management becomes a whole lot easier. Couple of simplified examples. So, for example, I give you the thing with the thermal slug. So this is a QFN 0.5 millimeter pitch, it's 700 by 700, edge by edge, 48 pins, and this is non-IPC. I added the suffix -T, which means thermal pad is 5.2 by 5.2 millimeter. So if I have flavors with different thermal pads, I can pick them up in my library. They have a unique name. I'm not going to end up with the wrong one on the board. Nut names, very interesting trick. I have two circuits. They're both of these nuts are reset bar. Yet on the board, they don't connect. Because Altium allows two different notations. You can have a leading backslash followed by a string, and that creates this beautiful overstrike. Or you can do it a different way, where you do R backslash, E backslash, S backslash. That's a different notation. The problem is when you spit out a net list, the ASCII strings are different. One ASCII string says backslash reset, the other ASCII string says R backslash E backslash whatever. So they do come in the PCB as two independent nets, yet on your schematic they look like the same net and you think that these two are actually going to be tied together. They won't. Don't use decorators in net names. Very dangerous, okay? And it gets worse if you have to hand off that data to other tools. They have their own fancy tricks. Same thing, another thing that can happen. If you look over here, it says magneto shutdown and sleep space N, but the lines are actually, or the wires are actually covering the underscore and the overstrike. Very dangerous. Somebody else is going to go, okay, I need to create a net called shutdown, not noting that it's actually shutdown bar. Don't do those things on net names. Sooner or later, you're going to get bit by that. Again, letters, numbers, nothing else, because anything else can or will be hidden and is going to disappear. Schematics. The internet is full of schematics that are horrible. Don't do that. I actually had to inject one more slide last night because I was browsing something and I found a prime example. This comes from a leading company which is like the most prominent company in the world when it comes to analog chips. They produced this one. This comes out of an application note. Good luck figuring out what is going where. It is basically a capacitor with two net names on it, another capacitor with two net names on it, another one with two nets on it. And then there is no way you can figure out what is going where. The computer can, and your connectivity is guaranteed. But a human, you're going to spend half an hour figuring out how that thing is wired. Don't do that. Net names are net names. They are there to name a net. They are not there to create implied connectivity. Don't use a net name over here and then use a net name over there. Yeah, the computer will connect them. But visually, it's bad. Draw the wire. Make clean schematics, you know. That's what schematics are supposed to look like. You make a hierarchical design. Everything is wired up. Signals leave schematics using ports. They don't go by a stub of wire with a net name and then go, okay, well, they'll get picked up somewhere else. No. Do it clean, because visually it is much, much easier to error check this thing than having to go and hunt for some missing connection. Put your mechanical parts on a separate sheet. Any nut, bolt, screw, mounting hole, whatever. I put those on a sheet. I wire them up. They're going to travel. They're going to be in my bill of material. They're going to be in my pick and place file because they will travel down to the board and in my output files. They won't be questions afterward. Where are the screws? Well, they are in the design. We know what they are. Okay. Another thing. So wires. That's connectivity. Net names, they only name a wire, a bus, or a bus entry. They are not used to create inferred connectivity. You use wires for that. Anything that leaves a sheet, use a port. Don't leave dangling nets. This kind of, that's unreadable. You can't visually debug that. You cannot vow for the integrity of this kind of design. Crossing lines. Altium has gotten better at that. When you're importing now something that has a junction, they actually do the thing where they break the wire and they show you you should clean that up. Don't do that. A T-junction is always a connection. A crossing line never connects. Those two golden rules, you're never going to end up where all of a sudden a short is being created, or worse, something gets broken. And then the other thing is that what you have to realize is that what we're dealing with in the industry is that a lot of the machinery that's used on the shop floor is very old and has extremely long lifespans. That drilling machine was decommissioned last year. It's run by a PDP-7 using 5-bit paper tape. Don't expect it to be able to read your whatever font set that is being used on Windows or Macintosh or whatever. It can't handle your files. Somebody will need to take a look at your data, manipulate it, tweak it to get that machine to read it. If somebody has to touch your data, somebody can touch it wrong. You're going to get a phone call. We have a production stoppage because something went wrong. If you set it up right in your library, if you set your input data up correctly, even that old machine won't have any trouble with your data. And then it all comes back, things to remember. Beware of the little things, paper copies, disappearing periods, dots, scaling errors, Beware of the man-machine issues, locales, Unix versus Windows versus Macintosh versus tablet operating systems. Graphical issues where overstrikes and underscore may be hidden by wires or other things. Make clean schematics. Don't use implied connectivity, and keep your library clean, because you do not want to end up with this. Because that's going to be a hell of a phone call solving that one. All right, questions?
I had a question about how do you define differential pairs in there?
Because there you need to use underscores. That is one of the situations where you use the underscore N and the underscore P. There's no escaping, but even when you do that, you still have to put that special marker. Altium has a special differential pair marker, so it becomes obvious. You keep those two together, that there's actually, because that's the visual cue for you that, okay, there's actually an underscore hidden by the wire. Yeah, sometimes, same thing with buses. If you have a like D0 to D7 and they're feeding into a bus, and you have to use the notation where it's D between square brackets, 0, period, those two periods get hidden. There are situations where you can't escape it, but you can derive it from the notation that something special is going on. Yeah, you can't always win.
Question about tolerances. You didn't show an example, say, for example, 0.1% tolerance. How would you do it?
So 0.1% tolerance, 0.1%. So the tolerance would be encoded as 0.1%. Because even, yes. No, I know, but even if that period disappears in that case, it's going to show up, the 0 is still going to be there. So that's going to be a visual cue that there's actually, normally a number doesn't have a leading 0. Even if the period disappears, the fact that you see 0, 1 or 0, 0, 1 means that, okay, something disappeared here. That's a visual cue. It's the trailing zeros that are a problem. Because if you encode it as, it's 10.00K, where the double 0 means it's implied to be a 1%. If now that period disappears, it's a 1 mega ohm resistor. If it was 3 trailing zeros, it becomes a 10 mega ohm resistor. And that's going to be a make or break situation. So those are the kind of things that you have to keep in mind when you're doing these kind of things, because ultimately all these things, they result in either a phone call, which is stoppage, or a board on the bench that you have to spend hours troubleshooting and then find out that there was nothing wrong with the design, just somebody stuffed the wrong part on the board because they read the number wrong. Not good if you have to go to the boss and explain that is what happened. So, things to think about. Yes?
Designators for jumpers, do you also put that?
J? Yeah. Yeah.
Okay, so
Yes. Because again, if you think about it, the jumper is the least movable part. It's a two-pin header. Now, if you're talking about the piece that goes on the jumper, the little black thingies that you stick on it, that will be P something.
Talking about just like a unpopulated.
Unpopular, yeah, exactly. Oh, if you're talking about like the 0 ohm resistors?
No, but you just want a jumper. Some of the argument is that they just solid blob on top of the resistor pad.
I have a special structure for that that has its own designator type.
Because the fat houses will pick that up and think that's a DNI resistor.
Yes,
Not populated.
exactly. So we actually have, one of the things that we do is when we're building boards, we like to inject 0 ohm resistors to be able to disconnect certain parts of circuitry that are under test. The problem is when we go to production, we don't want to populate them because they cost money. So I actually have a footprint that by default, it looks like an 0805 or an 0603 net tie. So it actually has 2 pads with a piece of copper shorted. So when you inject those in your schematic, they end up on the board as net ties. When it comes time to debugging them, the guy on the bench can take an X-Acto knife, cut them to isolate his circuit. When he wants to reconnect it, he solders a 0 ohm jumper on it. When we go to production, we don't have to touch the Gerber because the short is already on the board, and those shunts become do not install them. So we don't waste money. We don't have to redo the layout section. We don't waste money on injecting 0 ohm resistors. So it's a win-win situation. So that is some things you can kind of abuse a net tie into becoming a virtual component. So that's another trick. And then they would fall under the NT. They would become a net tie, giving again a visual cue when you're parsing your bill of material that for the final production, anything that is a net tie don't install that because there's no need to install it. It is already tied. And then if somebody needs to do the debugging, he can find where they are by just looking where are the net ties, and they highlight on your design. Exactly. You want to see if there's any return problems or signal. Yeah, exactly. You want to be able to, or you may have an input in a differential input pair. And you want to isolate some filter section that is in front of it. You inject those things. You can just cut them and hook up a network analyzer and characterize the filter on the board. When you're done, solder 4 0 ohm resistors, move on to the next block. So, tips and tricks to stay out of trouble.
How do you deal with diodes?
Diodes, in what sense?
Did you notice that pin 1 doesn't always mean cathode or
Correct. So I will. Correct. So, and the RGB LEDs where, yeah. So I have in my schematic library something called diode-1A2K, meaning pin 1 is anode, pin 2 is cathode. I also have diode-1K2A, or I have 1A3K. And then depending on which footprint, if I build my component, I pick the footprint if it's a SOP23, and then I have to go and find the symbol that maps the pins onto the footprint. So that has a unique name where basically the assignment of the diode onto the pins is encoded in the name of the component. So there's no ambiguity. I always know that this is going to match. Other things you can have, if you remember.
one problem I noticed in particular is communication. Sometimes the marker, when the guy goes on the machine and looks at the marker on the diode bar, it doesn't, will vary on the cathode or the anode.
Yes, so that is another thing that we commonly run into. We don't do, where I work, we don't do polarity markers anymore because our boards don't have silk screens. The density of the board is so high, there's no room for designators or ink on the board. We can't do it. So what we did is we used mechanical 13 as an assembly layer, and there the pins, actually what I do is on top of the pads, I show what the pads are as a rectangle. Pin 1 is a fill as opposed to just an outline. It has the number 1 in it, or it has a plus in it, or it has an A or a K in it. So whoever is assembling the board has to plot that layer to find out what all the pin 1s are. That's how we solved that one. And like I gave the example of an RGB LED, we do the same thing. I mean, those things have 6 pins. So you will find something called LED-RGB, and it'll say 1 BK for blue cathode, -2 red cathode, and so on, because every manufacturer has its own permutation. How do you keep them apart? That doesn't work. So by creating symbolic names that encode the pin map, you solve that problem. And if you think about it, that is actually, if you're doing any kind of simulation, when you're attaching model files, SPICE does that too, because SPICE gives you a pin map. It'll tell you pin 1 is VCC, pin 2 is the negative input for an op-amp. You have to encode that. I use a similar encoding in the name for my symbols. It solves these kind of problems. And
The footprint would look the same,
the footprint, the naming is different. Yeah. So I have, like I said, I have one SOT23 package in my footprint library, which has pin 1, pin 2, pin 3, but the schematic symbols have different pin mappings, but pin 1 is always pin 1. Now the other thing you want to do, that's something that I didn't mention, because this is not about data integrity. This is, if you're going to start doing things where you have variants in your design, let's say you have 2 different SOT23 footprints, and you create a variant in your design. If that is not pointing to the same physical footprint file, both footprints will be loaded on your PCB, and you will have to stack them on top of each other to do your layout. So you're going to get placement, DRC errors, you're going to get all kinds of stuff. So if you're going to make any kind of variance on a board, you have to be, all your symbols for which you have variance have to point to the same physical footprint file. Otherwise the tool can't resolve it.
Basically, you just have the pins that aren't actually out of
Exactly. So that is another thing, that don't have 23 permutations of a SOT23 in your library, because ultimately you're going to run into a situation where you have a bunch of stuff you have to stack on top of each other because it doesn't work. Keep your libraries clean, and the goal there is it's better to have more flavors of schematic symbols than flavors of footprints. You really should only have one 0603 resistor. You really only should have one. Well, capacitors is different because there's heights to play with, and your courtyard may change depending on the thickness of the package. So we actually have an 0603 dash, and we have 3 height flavors, because if you have the really tall ones, you're going to have shadowing effects, especially if you're going to send them through a wave. For reflow, it doesn't really matter that much, but if you have them hanging glued underneath a board, that thing is traveling through a wave, the thick parts have to be spaced further apart for the wave to be able to get in there. You're going to get problems during your during your assembly. So for that reason, we encode those thicknesses different. And there you sometimes have an issue where for a certain build that has to be a 1 microfarad capacitor, and there's a different variant with different timing where it's a 10 micro, and the footprint changed because the thickness changed and the courtyards are changing. What do you do with that? In that case, you have to go for the one that has the widest clearance, and that becomes a deviation in your board design. You can't always win. There's a lot of situations where you're going to go, we can't really solve that one, but try to minimize them, because it's, like I said, it never fails. You just send out Gerber, you send out your drill files, you're going home, 15 minutes later comes the email you didn't notice, and on Monday morning there's no boards. And then somebody has to be held accountable for how come that our quick turn, our 2-day quick turn became a 5-day quick turn. Well, because we goofed up in our data exchange. Not good.
So we have one solution we use variant for different channels. So basically for diodes, for the channel 1 we use compound semi, and then channels use
Somebody else.
I know the Altium doesn't really like that feature. It always pops up errors when you do that. Is there any reason why it comes up?
So are you talking about really where you have a schematic sheet and you make multiple instances of the same sheet? Yeah, there's no real solution for that. What you have to do is you have to, if you have to do that, you would have to have one master sheet with the on-semi part, and then another one with, let's say, a diode, a TI part, and then you make multiple instances of the sheet that has a TI part. There's no way, yeah, that is not, you can't really do that. That doesn't work. Yeah, that's not a, there are limits to what you can do. You cannot always win. You can try to win as much as you can, but you can't always win. All right?